Welcome back to the Deep Dive, where we cut through the noise and get straight to the insights that matter most to you. In a world just, well, awash with information, our mission is to deliver those aha moments, giving you that shortcut to being truly well-informed. Today, we're plunging into a topic that's not just at the cutting edge of technology, but one that could fundamentally change how we build and interact with artificial intelligence. Neuromorphic computing. We've got a fascinating stack of sources, including a pretty comprehensive paper from Nature titled Neuromorphic Computing at Scale, to guide us through this.
Indeed. And our deep dive today is really all about understanding this brain-inspired approach, what it is, its incredible potential, and also the significant hurdles it still needs to overcome to move from the lab into, well, widespread real-world applications. We'll explore what scaling truly means in this context and why it's such a critical dimension, really, for tracking progress in this revolutionary field.
That's right. Think of it as maybe dissecting the very blueprint of the future of AI. Inspired by the most complex, efficient, and adaptable intelligence system we know, which is, of course, our own brains. We'll unpack some surprising facts, look at the grand vision for a whole new era of computing, and tease out what this could mean for, well, everything. From tiny, always-on sensors maybe in your home to massive supercomputers tackling humanity's biggest scientific challenges. This feels like more than just a technological upgrade. It's a fundamental reimagining. And as we delve deeper, I think we'll uncover some truly surprising implications. Okay, let's unpack this a bit. In an era where our deep learning models are achieving these incredible feats, seemingly pushing the boundaries of what traditional digital computers can do, why are researchers still looking to the human brain for inspiration? What makes our biological wetware, our brains, such a vibrant, maybe even indispensable source of computational prowess that it demands a whole new computing paradigm? It feels like we've made so many strides with traditional digital computers, right? So why turn to biology now?
Yeah, that's a crucial starting point. Because despite the incredible leaps we've seen in deep learning and traditional AI, the human brain remains completely unmatched in its efficiency, its adaptability, and especially for tasks that have real-world constraints, size, weight, and power constraints. Neuromorphic computing is precisely this brain-inspired approach looking at hardware and algorithm design, aiming to efficiently realize artificial neural networks by applying these principles of biointelligence. I mean, consider this. Your brain operates on roughly 20 watts of power. That's less than a dim light bulb. While a modern AI supercomputer, maybe training one of these huge language models, can consume megawatts, enough to power a small town.
Wow.
That's just orders of magnitude difference in efficiency, often requiring massive cooling systems too. And the fundamental inspiration here comes from contrasting the brain's parallel in memory processing with the von Neumann architecture that dominates conventional computing. In a von Neumann system, computation and memory are physically separated.
Right, the standard setup.
Exactly. So data has to constantly be shuttled back and forth between the central processing unit, the CPU, and a separate memory unit for almost every single operation. This constant back and forth is known as the von Neumann bottleneck, and it's incredibly energy intensive and, frankly, slow. It often consumes 90% or more of the total system energy just moving data around.
90% just moving data?
Yeah, it's huge. It's like, imagine a chef who has to walk across the kitchen to a pantry for every single ingredient, then walk back to the stove only to repeat the process for the next step. It's just inefficient. It's slow. The brain, on the other hand, performs computation directly where the data is stored and processed within the neural and synaptic connections themselves. So it's like that chef having all their ingredients and tools right there on their cutting board where the work happens directly. This allows for massively parallel operations with extreme efficiency, completely avoiding that bottleneck. And that core difference is really what neuromorphic computing tries to emulate in silicon.
That's a really powerful distinction. So it's not just about raw computational speed, clock cycles per second, but about how elegantly and efficiently the brain handles information, especially with those real-world constraints.
This sounds like more than just a theoretical concept for scientific papers, then. Is this something with real commercial traction, or are we still talking purely academic research? What does the future hold for this field, in terms of market impact and practical deployment?
The potential is enormous, yeah. And it's definitely moving beyond just the academic sandbox. Extrapolation suggests an expected market for neuromorphic computing chips could reach a pretty significant US $556.6 million by 2026.
Good, that's not small change. No, it's not. And we're already seeing some of these chips entering early-stage commercial markets. They're demonstrating capabilities to solve complex computational tasks with incredibly low power budgets and latency. Think about real-time analytics in tiny edge devices, maybe, or always-on sensor processing without just draining batteries constantly. And unlike traditional computing, which often specializes, you know, either massive exascale supercomputers or very small-scale embedded systems, neuromorphic computing shows this unique potential to be disruptive in both classes simultaneously, using a remarkably homogeneous, sort of consistent computing technology throughout.
So the same basic tech could scale way up or way down.
Exactly. This versatility, the ability to scale up to massive data centers or down to tiny edge devices with the same core brain-inspired technology, that's a major driver of its growth and market appeal. It's really a unifying approach.
You mentioned earlier a potential AlexNet moment for neuromorphic computing. For you, the listener who might not be familiar with that specific event, could you explain what that was? And why is that comparison so significant for understanding where neuromorphic computing might be headed? It sounds like a really pivotal point in tech history.
Absolutely. Yeah, the AlexNet moment, it refers to a breakthrough that essentially catalyzed the deep learning revolution we're still experiencing. Back in 2012, there was this convolutional neural network called AlexNet. It leveraged powerful GPUs, graphics processing units, and a large data set. And it dramatically outperformed all existing methods in a major image recognition competition, like blew them out of the water.
Right, I remember that buzz.
Yeah. It wasn't just some small incremental improvement. It was a clear, undeniable demonstration of what deep learning could do, a moment that just grabbed the world's attention. That single event inspired massive scaling, unprecedented investment, and this wave of innovation that we're still riding today. Neuromorphic computing, well, it feels like it stands on the cusp of its own such moment. It's about achieving a clear, demonstrable milestone, maybe solving a previously intractable problem with orders of magnitude less power, or enabling a truly adaptive, continually learning system in a way traditional AI just can't. Something that inspires that kind of widespread scaling and investment. Our sources highlight that identifying the open issues, the challenges we'll talk about, and diligently resolving them, that will usher in transformative impacts comparable to deep learning's rise. So for you, the listener, the significance is this. We're talking about a technology that's really primed for a breakout, a point where its undeniable practical advantages become so clear that it unlocks its true widespread potential. And that paves the way for much larger, more integrated deployments in our everyday lives.
Okay, so as we delve deeper into this brain-inspired approach,
Yeah.
what are the specific architectural advantages? You mentioned avoiding the von Neumann bottleneck. What else do neuromorphic systems offer over, say, the deep learning accelerators we're all familiar with today, like those GPUs that powered AlexNet? What makes them fundamentally different and, uniquely suited for certain tasks where traditional systems might struggle?
Right. Well, the most significant advantage, as we touched on, is how they fundamentally tackle that bottleneck. The memory and compute are tightly coupled. To go back to that chef analogy, imagine a traditional computer constantly fetching ingredients from a separate pantry for every single step, then storing the partially prepared dish back in another pantry. That's the von Neumann bottleneck data, constantly moving between processor and memory. Slow, energy hungry.
Wow, constant fetching.
Exactly. Neuromorphic systems, by contrast, are designed to avoid this costly, energy-intensive data transfer. They integrate computation directly within the memory elements. So, like the chef who has everything right there on their cutting board and does all the work there, this allows computation to happen directly where the data resides, dramatically cutting the energy and time spent just moving information around. For tasks that require massive data movement, like processing continuous streams of sensor data or complex pattern recognition, this architectural difference offers just immense benefits. Power, latency, throughput, all improved. And beyond this inherent memory compute coupling, neuromorphic systems boast several other really distinct computational advantages. These are critical for efficiency, adaptability, and real-time responsiveness. First, they use sparse distributed information encoding. What does that mean? Well, information isn't represented by dense, continuous streams of data, like a constant video stream that uses bandwidth even when nothing changes.
Like a security camera recording an empty room.
Precisely. Instead, information is communicated through discrete spikes or events that inherently carry temporal information. Timing matters. Computation only happens when an event occurs, which is incredibly efficient. Think of it like your brain again. Instead of constantly processing every single pixel in your field of vision, it sends a signal only when something changes a movement, a shift in light. This event-driven approach leads to extreme efficiency. The system only expends energy when there's relevant information to process. Unlike traditional systems that are often constantly crunching numbers, even if those numbers are redundant. Second, these systems support dynamic and local learning. Most deep learning models today rely on something called backpropagation.
Right, the standard training method.
Yeah, and it requires global updates across many layers, vast data transfers, and significant power to compute gradients across the entire network. It's a very coordinated, top-down process. Neuromorphic systems, inspired by the brain's plasticity, its ability to change, enable learning to occur dynamically and locally, right at the individual neuron and synapse level. This means small, continuous adjustments can happen throughout the system in response to new information, rather than these massive, coordinated, power-intensive reevaluations of the whole network. This is crucial for things like lifelong learning, adapting to new environments without needing to be retrained completely from scratch every time. Third, to achieve stable perception as they learn, these systems actively make predictions about sensory signals.
Predictions, how does that work?
Well, it means they're not just passively receiving data, they're constantly generating internal hypotheses about what they expect to sense next. When the actual sensory input arrives, they compare it to their predictions. This predictive processing helps them integrate new information more effectively, filter out noise, and maintain a stable understanding of their environment. It's a much more active and robust form of perception. And finally, they operate with dynamics on several timescales. This feature allows for real-time learning and processing crucial for adaptive applications in dynamic environments. Imagine a robotic arm that needs to react instantly to a sudden obstruction, like something falling, while simultaneously learning a more efficient long-term strategy for grasping objects. Neuromorphic systems can handle these simultaneous short-term reactions and long-term learning dynamics.
So what does this all mean for you, the person trying to get more from your devices or understand the next generation of AI? It sounds like these aren't just minor improvements, not just tweaks to existing architectures, but fundamental shifts, really, inspired by how evolution solved similar problems in biology. The core insight here isn't just that it's potentially faster, maybe, but that it's fundamentally smarter about how it uses energy and adapts, almost thinking more like a living system. Is that the biggest takeaway for someone trying to grasp its unique power?
Precisely. You've absolutely hit on the central point there. These features aren't some magical solution that just came out of nowhere, nor are they just incremental engineering improvements. They are deeply inspired by how biology has solved these problems over millions of years through processes like self-organization, dynamic rewiring of connections, three-dimensional growth, modularity in brain regions, and incredibly efficient signal encoding. The promise is that these biological principles can directly inspire the design of large-scale, highly efficient artificial systems, systems that can operate with unprecedented power efficiency and adaptability. It's really about taking cues from nature's ultimate computer, the brain, and translating those elegant solutions into silicon.
We keep emphasizing at scale throughout this deep dive. When we talk about neuromorphic computing at scale, what exactly does that entail? Is it just about cramming more neurons onto a chip, or is there a deeper meaning here about its impact and deployment?
Yeah, that raises an important question because neuromorphic computing at scale is a really comprehensive concept. It goes far beyond simply having more transistors or more simulated neurons. We define it as a systems capacity, and this encompasses everything from algorithms and hardware to architecture and infrastructure. Its capacity to operate at the size, speed, and energy efficiency required to address complex, real-world tasks.
Okay, so it's about practical capability.
Exactly. It's about moving beyond interesting lab proofs of concept, which are absolutely critical for initial research, don't get me wrong, but moving towards deployment that can solve problems on a societal level. This isn't just about raw numbers, it's about practical, widespread impact. This widespread adoption could manifest in various ways, maybe large virtual systems accessed in cloud data centers, or vast networks of distributed edge devices exhibiting collective intelligence, or some combination of both. The key here isn't just technical capability, but enabling widespread adoption by millions of users, knowingly or unknowingly, really integrating these systems into our daily lives, powering everything from smart appliances to autonomous vehicles. And what's particularly interesting, maybe even counterintuitive for some, is that despite its fundamental differences from conventional von Neumann designs, neuromorphic architecture is actually ideally suited for high-performance computing, or HPC, environments.
Really? How so?
Well, it means the same basic neuromorphic system could potentially manage large-scale scientific simulations. Think complex physics, climate modeling, drug discovery, and also handle tiny-scale edge intelligence configurations. For example, in smart sensors monitoring infrastructure or wearables tracking health data. This remarkable versatility, being effective at both extremes of the computational spectrum with a unified technology, that's a significant differentiator and a major driver for its potential future.
So if I'm getting this right, we're not talking about specialized hardware that only works for one specific niche, like GPUs being great for graphics but less so for other things. You're saying a single coherent neuromorphic architecture could potentially power a massive supercomputer simulating, I don't know, quantum mechanics, and simultaneously process audio commands on your smart speaker with incredible efficiency.
That's truly remarkable flexibility.
Exactly. It's about a fundamental design philosophy, one that lends itself to a wide range of computational problems, from the very large to the very small, efficiently addressing those size, weight, and power constraints across that entire spectrum. Okay, so if we're charting a course for these massive brain-inspired systems, what are the essential features that developers and designers need to bake in? What's the fundamental DNA, if you like, of a truly scalable neuromorphic system? The kind that will move us beyond prototypes and into widespread adoption.
Well, it's not just the core neuromorphic features we've already discussed, like the event-driven processing and local learning. It's a set of additional characteristics that are absolutely essential for achieving true scale. These features augment the fundamental principles by drawing even deeper inspiration from the brain and its intricate neural processes, allowing us to build systems that are not only efficient, but also robust, adaptable, and capable of solving complex, real-world problems. Let's start with brain-inspired organization, hierarchy, and sparsity. Just like the brain's visual cortex, which processes information in a layered hierarchical fashion, detecting edges, then shapes, then objects, organizing neural computing into hierarchies helps disentangle complex inputs and information at different scales. This means each hierarchical level can be assigned to deal with a different level of information complexity. It gives you better granular control, increases explainability within large models, you can sort of see where decisions are being made, and reduces redundancies that can plague simpler networks.
Like breaking down a big problem into smaller steps.
Exactly. Think of it as breaking down a truly complex problem, like understanding a dynamic, real-world scene, into smaller, more manageable sub-problems that build upon each other logically. Then there's sparsity. This is a really notable factor in the brain's incredible scalability and efficiency. Studies have shown that human brains, as they develop, start with relatively sparse synaptic connections, then they experience a period of densification, and then they undergo extensive pruning, cutting back connections to maintain a relatively constant level of sparsity throughout life.
So less is more, in a way.
In a very important way, yes. In neuromorphic systems, this translates to reduced representational complexity. That means significant improvements in computation, storage needs, and energy consumption without necessarily losing accuracy. And neuromorphic systems inherently benefit from sparsity because of their event-driven communication. Neurons only fire when there's relevant information. This further boosts efficiency by minimizing unnecessary activity. This inherent sparsity also opens up possibilities for using, maybe, unconventional spatial layouts of computing devices, potentially making the slope of model scaling even steeper and more flexible. Next, we need to consider neuronal scalability. This just refers to the ability to support a large number of neurons on single or multi-chip systems. Why does this matter so profoundly? Well, this capability is what enables deep spiking networks or rate-based algorithms to tackle complex real-world machine learning problems that require immense processing power. Things like advanced pattern recognition, natural language processing, complex control systems for robotics. And crucially, it also offers the ability, potentially, to simulate full human brain simulations in real time.
Which is a huge goal in itself.
A massive goal, a game changer for cognitive applications in neuroscience research. It allows scientists to test hypotheses and observe brain-like dynamics in a way that's currently just impossible with traditional computers. Our sources show remarkable progress here. Current systems like Intel's Loihi and the University of Manchester's Spinnaker already support hundreds of millions of neurons, and the field anticipates systems with more than 10 billion neurons by 2026.
Wow. 10 billion. That's a staggering leap. To put that in perspective for you, the listener, simulating a full human brain isn't just about understanding intelligence abstractly. It could unlock entirely new avenues for medical research, personalized therapies, even fundamental questions about consciousness. What kind of impact could a system with 10 billion neurons capable of real-time brain simulation really have on fields like neuroscience and medicine?
Oh, the impact would be absolutely revolutionary. Consider the Markram cell study you mentioned earlier. It used, what, the 100th largest supercomputer at the time to simulate just over 31,000 neurons. The human brain contains roughly 1 million times that many neurons, so the scale needed is just immense.
Mind-boggling numbers.
They really are. Systems like Spinnaker 2 and Loihi 2 are specifically designed to flexibly simulate neural behavior at numerous levels of abstraction, from very detailed models to more simplified ones. They offer that pathway to bridge this gap. For neuroscience, it means potentially building digital twins of parts of the brain, testing interventions for neurological disorders like Alzheimer's or Parkinson's in silico on the computer, identifying biomarkers, or even developing truly personalized treatments based on a simulation of a patient's unique neural dynamics. It moves from just hypothesis to direct dynamic simulation. Okay, then there's a need for dynamic and flexible architectures. The brain is inherently dynamic, right? Executive cognition, things like planning, decision-making, requires highly evolving and dynamically reconfiguring networks of brain regions. They interact in complex and transient communication patterns. To mirror this, neuromorphic systems are designed to support dynamic reconfigurability. This allows for plasticity changeability in the primitive building blocks, like synapses and neurons, or even the entire system's connectivity.
So the hardware itself can change how it's wired up.
On the fly, essentially, yes. This means the system can adapt and reconfigure its connections dynamically, much like how our brains adjust to new information or tasks, or how a single cortical region in the brain can sometimes shift its function based on the current cognitive demand. For example, some neuromorphic chips can quickly reconfigure their synaptic connections to perform vastly different tasks, maybe switching from doing linear filtering on sensor data to doing edge detection, or even learning a new pattern without extensive retraining. Alongside this, many neuromorphic chips use asynchronous communication protocols like address event representation, or AER. Unlike traditional synchronous systems that rely on a global clock ticking away, driving everything at the same pace regardless of activity, AER is event-based. Data is only sent when a neuron spikes or an event occurs. This minimizes idle power consumption and allows different parts of the chip to operate at their own natural pace. It's a hallmark of efficiency, and it's evolved from first-gen silicon retina systems to the sophisticated cortical cognitive processors we see emerging today. And finally, we need robust system-level integration and awareness. This is crucial for real-world use. To achieve widespread adoption and functionality, these systems must allow for heterogeneous integration. That means combining a wide variety of computing resources and neuromorphic elements, and also seamlessly integrating with external tools and sensors. This allows for combining different device technologies, maybe traditional CMOS, with emerging memristors on a single chip. It allows fusing data from numerous different sensors and deploying hybrid AI frameworks that blend traditional and neuromorphic approaches for optimal performance. This is absolutely critical for real-world scenarios where you have diverse inputs.
So mixing and matching technologies.
Exactly. And for end-to-end applications, sensor and compute interfaces are critical. This involves efficiently translating non-spike-encoded commercial sensor data, like from a standard camera, into spike-encoded formats that the neuromorphic chip can understand. Imagine converting a standard camera's continuous pixel data into these discrete events. Furthermore, the development of specialized neuromorphic sensors, things like event-based cameras that only report changes in light, or epidermal layers for prosthetics that mimic skin's sensory capabilities, can further boost real-time response by generating spike-based data directly at the source.
Cutting out the translation step.
Right. And lastly, systems must be designed with resource awareness. That's the ability to track and dynamically assign resources, energy, compute, memory based on changing goals or conditions. This capability, inspired by self-aware architectures, ensures efficiency and versatility over the system's lifetime. For instance, a smart camera on a drone might dynamically allocate more processing power to object recognition when it's actively identifying a target, and then shift down to low-power environmental monitoring when it's just cruising, all based on its current mission objectives and maybe its remaining battery life.
So what's really fascinating here, it seems, is that while some of these individual design concepts, extreme parallelism or hierarchical organization, aren't entirely unique to neuromorphic computing, it's their interplay. How they work together within a unified, brain-inspired computing model that truly offers this revolutionary potential. This isn't just about incremental gains. This could enable us to deploy much larger models, or perhaps even many smaller, more specialized, task-specific models, breaking free from the current trend of training one extremely large, energy-hungry model for pretty much all tasks. It really feels like it redefines what intelligent hardware can do, moving towards a much more efficient and adaptable form of AI. Okay, this all sounds incredibly compelling, almost like science fiction becoming reality. But let's be real, it's clearly not a simple task to achieve this vision. What are the significant hurdles? What are the roadblocks that the neuromorphic community needs to overcome for widespread adoption? Where are the friction points in turning this grand vision into everyday reality? And what might slow down its progress?
You're absolutely right. The path forward is complex. And if we connect this to the bigger picture, despite the immense potential, there are several roadblocks affecting hardware designers, users, algorithm developers, everyone involved. A fundamental challenge, for instance, just remains our limited understanding of the brain itself.
Right. We're trying to copy something we don't fully understand.
Exactly. It's a bit like trying to reverse engineer an alien supercomputer with only partial blueprints, which is inherently difficult. Though it's important to note, neuromorphic computing itself might actually help us improve that understanding. As we build more sophisticated models and simulations, we learn more about the brain, creating a kind of positive feedback loop. But it's still a challenge. One major hurdle is what our sources call the co-design conundrum. Neuromorphic computing is inherently interdisciplinary, right? It bridges neuroscience, computing, engineering, AI. This naturally leads to varied approaches to system design, which can introduce significant inefficiencies if not managed carefully. You have top-down approaches, where researchers might abstract cortical layers and brain functions to guide the hardware design, focusing on high-level biological principles. Then you have bottom-up approaches, which leverage specific device characteristics like how a new type of memory works at a physical level to drive algorithmic advances.
So starting from the brain versus starting from the silicon.
Pretty much. The problem is, without really close coordination, these approaches can diverge. For instance, a device engineer might optimize a new memristor for one specific electrical property, completely unaware that an algorithm developer actually needs entirely different dynamic characteristics for their spiking neural network to work well. Conversely, an AI researcher might demand capabilities that the hardware simply can't efficiently deliver with current physics or materials. Both scenarios introduce inefficiencies due to this lack of awareness between device properties and algorithm design. The solution, our sources strongly suggest, is a rigorous hardware-software co-design approach, where these aspects are developed in tandem, hand in hand, with scalability baked in right from the very beginning. This ensures that the hardware capabilities align perfectly with the algorithmic needs and vice versa, avoiding costly rework and maximizing overall efficiency.
Okay, so that's a system-level challenge. Now, for you, maybe a developer listening to this, someone wanting to dive into this field, what are the practical pain points? Is it as easy to get started with neuromorphic computing as it is with mainstream AI frameworks like, say, PyTorch or TensorFlow?
Yeah.
Those have huge communities, extensive libraries, well-defined workflows.
Not yet. Unfortunately, no. This is where a significant software gap exists, and it's highlighted in some of our source figures. Developers currently often need to understand really intricate, low-level hardware details, things like individual neuron parameters, synaptic weight distributions, complex spike routing mechanisms. It creates a really steep entry barrier.
So you need to be a hardware expert and a software expert.
Almost, yeah. Or at least have a much deeper understanding of the hardware than you typically need for mainstream AI. We desperately need a higher-level coding abstraction. We need to move from the sort of assembly-like coding, where you're practically dealing with individual gates and memory addresses, to more object-oriented approaches. Approaches that allow developers to think about neural networks at a more conceptual level, focusing on the functionality, what the network should do, rather than the minute implementation details of how it does it on a specific chip. The challenges here are manifold. The sheer diversity of neuromorphic hardware, different companies building different chips with different architectures, makes replicating models across different platforms incredibly difficult. This often leads to hardware-dependent algorithms that aren't portable. You train a model for chip A, it won't run easily, or maybe at all, on chip B.
A vendor lock-in, essentially.
It can feel like that, yeah. There's a pressing need for common standards for both hardware interfaces and software APIs. Plus, we need an abstraction layer that allows a kind of compilation scheme for porting spiking neural network SNN models to any architecture, much like how traditional code can be compiled for different processors and operating systems today. Beyond this, basic quality-of-life tools that mainstream AI developers just take for granted. Things like inference optimizers to make models run faster, drag-and-drop editors for visually designing networks, comprehensive debugging tools, cross-platform compatibility. These are largely absent or still very nascent in the neuromorphic space. Also, for seasoned developers in large enterprises, integrated cloud scaling, deployment tools, and lifecycle management resources are critically missing. This makes it really hard to develop, deploy, and manage neuromorphic applications at scale. While mainstream AI frameworks achieved interoperability with formats like ONNX, allowing models to be easily exchanged between different tools, SNN frameworks still largely lack this shared standard. The community urgently needs to unite around open source frameworks and common intermediate representation levels to truly foster collaboration and broader adoption.
So for someone wanting to learn or get involved, it sounds like there's a significant entry barrier. It requires not just learning new skills, but adopting a fundamentally different way of programming these neural primitives. It's almost like learning a new language from scratch for a completely different kind of machine.
Precisely. There's a need for a strong theoretical foundation on how to use these neural building blocks effectively for computation. It's not just about taking existing deep learning models and trying to make them spike. It's about understanding how to leverage spikes, sparsity, timing, and local learning for entirely new computational paradigms. For instance, how do you best encode complex sensory information into efficient spike trains? How do you perform robust pattern matching using only event-driven data? Initial theoretical work has been seen in mathematical approaches like the Neural Engineering Framework, or NEF, which provides a principled way to build large-scale functional brain models. But much more development is needed to make this kind of thinking accessible and intuitive for a broader developer base, translating these complex neuroscientific principles into usable programming abstractions.
Okay, moving on to another challenge. If neuromorphic computing is so promising, with all these potential advantages in efficiency and adaptability, why aren't we seeing more widespread investment and adoption outside of dedicated research labs? What's holding users and investors back from pouring billions into this? Maybe similar to how other emerging tech fields like quantum or even earlier AI attracted massive capital.
Yeah, that raises a critical question for the industry's growth. A substantial challenge for potential users and investors is identifying appropriate applications where neuromorphic computing offers a clear, quantifiable, and perhaps provable advantage over existing, well-understood technologies. Our sources draw an interesting analogy here to quantum computing. Quantum attracted billions in financing partly because of formal complexity proofs, like Shor's algorithm for factoring large numbers.
Right, the promise of breaking encryption.
Exactly. That algorithm provided a clear, undeniable mathematical demonstration of quantum computing's theoretical superiority for a specific, highly important problem, even if the hardware wasn't fully ready to execute it at scale yet. Neuromorphic computing, despite having the ultimate existence proof, the human brain as an incredibly efficient computer, often lacks this type of formal theoretical advantage for specific, important problems that are easily benchmarked in traditional ways. This absence of clear mathematical proofs of superiority for widely understood computational tasks has certainly affected investment levels, because it makes it harder to pitch a clear, predictable return on investment. Furthermore, many of the tasks where neuromorphic computing really excels, things like lifelong or continual learning, robustness to noise and variability in real-world data streams, or ultra-low power machine learning using real-time sensor data, these are inherently difficult to break down into mathematically provable, easily benchmarkable sequences.
How do you benchmark adaptability easily?
Exactly. These are complex, adaptive behaviors, not easily reduced to a single, simple, comparable metric like floating point operations per second or accuracy on a static data set. Plus, to truly have meaningful closed-loop benchmarks for these tasks, where the system interacts with an environment, neuromorphic chips need to seamlessly interface with sensors and actuators, processing data and reacting in real time within a dynamic environment. This also requires significant standardization, right? From low-level electronics and spike coding schemes all the way up to high-level communication protocols between sensors, chips, and actuators. Without these clear, standardized, and easily comparable benchmarks, it's just hard to objectively compare different neuromorphic systems with each other, let alone demonstrate their advantages conclusively over traditional systems. And that makes investment decisions and widespread adoption much harder for companies looking for that clear ROI.
Okay, so we've laid out some significant challenges. The co-design conundrum, the software gaps, the benchmarking difficulties, even our own limited understanding of the brain. But where do the biggest opportunities lie now? And what concrete steps can the community take to foster growth and prepare for truly large-scale neuromorphic systems? It can't all be roadblocks, surely. There must be clear pathways to success here.
You're absolutely right. And what's fascinating here is that despite these challenges, the field has matured significantly beyond just academic prototypes. We're now seeing production-level systems with event-driven processing, increasingly sophisticated learning models running on them, and design tools that are enabling real-world experimentation. The foundational technology is becoming much more robust. So now is really the critical time to coalesce efforts to bring things together and build out a truly robust ecosystem that can bring neuromorphic computing to the masses. One crucial area is fostering research and development more broadly. We need to grant early and easy technology access to R&D groups beyond the traditional neuromorphic ecosystem.
Bring in fresh eyes.
Exactly. Think of it as inviting new players to the game, bringing in fresh perspectives and potential applications from diverse fields like robotics, bioinformatics, industrial automation, maybe even finance or logistics. Incentivizing these groups, maybe with awards, competitions, common benchmarks, and robust support through specialized workshops like Telluride and Capocaccia, or industry initiatives like the Intel Neuromorphic Research Community, INRC, creates a powerful multiplier effect. It rapidly propagates the advantages and potential of this new approach. Another key is developing impactful proofs of concept. Industry-specific proofs of concept are crucial because they serve as a tangible vehicle, a concrete demonstration of real-world benefits like energy efficiency and performance within a specific business context. The key here is selecting niche areas initially that can create a ripple effect. For example, designing an energy-efficient neuromorphic solution for a technical service provider that handles conversational AI engines. That will have a much broader impact, potentially reaching many end users through that provider than if you just design it for a single end user application initially. And importantly, these prototypes should ideally be built at scale from the beginning, not just incrementally, to truly showcase their potential and demonstrate real-world viability. Show what's really possible. Finally, maintaining recursive feedback loops, actively listening to early adopters and users is absolutely essential. This helps continuously improve research methods, shape the next generation of proofs of concept, and evaluate how the technology is actually being adopted and used. This user-centric approach ensures that practical application drives development rather than just theoretical ideals. Next, we must focus intently on enabling software and standards. This is paramount, as we discussed. We need easy, common, and preferably open source software. Particularly, we need compilers that allow mainstream users, those folks familiar with PyTorch or TensorFlow, to deploy models on neuromorphic platforms without needing to become experts in low-level hardware details. Cross-compilers, permissive open source licenses like Apache 2.0, and common frameworks significantly reduce individual software development efforts and dramatically boost community engagement and collaboration. Share the load, share the progress.
Lower the barrier to entry.
Precisely. Benchmarks also remain a crucial and active area of research. As we said, due to the inherent heterogeneity of neuromorphic systems, a diversity of metrics and benchmarks is needed, not just one size fits all. We can't compare apples and oranges with a single metric. While it's complex, collaborative efforts like NeuroBench are actively working towards defining collaborative, fair, and representative benchmarking suites. These encompass a range of tasks and metrics suitable for neuromorphic systems, looking at energy, power, latency, accuracy, robustness, maybe even learning speed. Establishing standards for event-driven interfaces and hardware-agnostic software stacks is really paving the way for defining fair comparisons across different hardware platforms. Lastly, we must address field-crossing technology by minimizing those interest losses we talked about. These losses happen during the bidirectional conversion between traditional data formats and neuromorphic spike-based formats. They often relate to suboptimal spike coding schemes. For instance, if you convert a standard image into a stream of spikes inefficiently, you might waste so much energy in the conversion that you negate all the energy benefits you were hoping to get from the neuromorphic chip itself.
So the bottleneck just moves to the input-output.
Potentially, yes. Addressing these interface issues is critical to ensure the seamless usability of neuromorphic platforms. The computational benefits achieved by these brain-like engines could be severely hindered by poor or lossy interfacing with the conventional digital world. Okay, looking towards future horizons, neuromorphic computing offers immense potential across several key domains. For neuroscience exploration, as we discussed, it's becoming absolutely essential for brain-scale simulations. Consider the virtual brain model again. It incorporates complex biological details of brain activity, but is incredibly difficult to simulate on GPUs in real time due to the sheer number of interacting elements and the communication overhead. Neuromorphic systems, with their inherent parallelism and in-memory compute, can potentially make these large-scale, detailed simulations possible. This leads to significant potential medical applications, like personalized Alzheimer's disease detection or treatment planning.
Like a flight simulator for the brain.
That's a great analogy, yeah. Researchers could simulate patient-specific neural network degeneration patterns, test the efficacy of different drug interventions in silico before clinical trials, or identify early biomarkers of neurological diseases by observing subtle shifts in simulated brain activity. And just to reiterate the scale challenge, the Markram study simulated 31,000 neurons. The human brain has roughly 1 million times that many. Systems like Spinnaker 2 and Intel's Luihi 2 are designed specifically to flexibly simulate neural behavior at numerous levels, offering that pathway to truly understand the brain at scale. For machine learning innovations, neuromorphic systems at scale are poised to drive entirely new, neuro-inspired algorithms, moving beyond the current deep learning paradigm in some ways. The key features we discussed earlier, sparse encoding, local learning, dynamic reconfigurability, temporal processing, they provide a kind of blueprint for what future ML innovations might look like. This represents a significant potential shift towards understanding algorithms and architectures as inherently interconnected, mirroring the brain's integrated design, rather than the isolated sequential approach typical of von Neumann computing. Our brains exemplify learning algorithms where parameters adapt constantly to modify functionality across several timescales, seamlessly blending computation and memory for continuous adaptation. Neuromorphic computing, especially by leveraging emerging device technologies, offers a distinctive solution to address these fundamental bottlenecks that currently limit traditional ML from achieving truly lifelong adaptive intelligence in the same way. And speaking of those emerging devices and architectures, efficient memory technology is absolutely critical to the scalability of neuromorphic systems. Memory is fundamental from information storage to consolidation and retrieval. It's the foundation for learning. Emerging memoristive devices, this is a class of devices including things like resistive RAM, spintronic devices, ferroelectric transistors, and phase change memory, they hold immense promise.
The memristors, that's memory plus resistor, right?
Essentially, yes. They have properties of both. These devices offer non-volatility, meaning they retain information even when the power is off. Unlike the volatile DRAM in your computer that forgets everything instantly, they also offer potentially very high density and multi-state properties.
Multi-state, meaning more than just 0 or 1.
Exactly. A single tiny component, a single memristor, might be able to store multiple distinct values, not just on or off. This makes memory incredibly dense and efficient, much like how a synapse in your brain can have varying strengths, representing different weights. Crucially, an array of such devices can implement the core multiply-accumulate operation, which is the fundamental calculation in neural networks, directly through physical laws like Ohm's law, right within the memory array itself. This leads to incredibly compact and low-power implementations of computation in memory. The desirable characteristics we look for in these emerging memories include incredibly low energy consumption, often measured in femtojoules, tiny fractions of a joule per bit, low latency, low operating voltages, high endurance, meaning they can be written to many times, high data retention, and importantly, seamless integration with existing CMOS manufacturing technology. Now, while challenges certainly exist, things like device non-idealities, they don't all behave perfectly identically, and integration difficulties, what's fascinating is that some of these non-idealities can actually be exploited as features.
Turning bugs into features.
Kind of, yeah. For instance, inherent device variability across an array, which might be seen as a flaw in traditional digital computing where you want perfect uniformity, can actually aid Bayesian computation, making probabilistic models more robust and perhaps more brain-like. Similarly, the internal dynamics that cause some devices to exhibit volatility, tendency to forget over time, can potentially be used for things like real-time motion detection or online learning, where having a transient fading memory is actually an advantage. As technologies like RAM continue to mature, their non-volatility and compute and memory capabilities are becoming increasingly attractive for applications constrained by size, weight, and power, pushing the boundaries of what's possible at the edge and beyond, enabling truly intelligent, autonomous devices.
We've really embarked on a deep dive today. From the fundamental inspiration of the human brain and the intricate hardware features trying to mimic it, to the daunting challenges that lie ahead and the immense opportunities for scientific and technological breakthroughs in neuromorphic computing. It's really clear this field isn't just about making faster computers. It's about fundamentally rethinking how we build intelligence right from the ground up.
Indeed. And we were at a critical juncture. The sources really emphasize that there probably won't be a single one-size-fits-all solution for neuromorphic systems at scale. Instead, we'll likely see a diverse range of hardware solutions emerging, each tailored to specific application needs, from ultra-low power edge devices that might live in your sensors to massive data center accelerators for large-scale simulations. The path forward seems to involve two crucial threads weaving together. First, developing robust, distributed, and asynchronous models that truly mimic the brain's operational efficiency. And second, scaling these learning models to vast networks and machines, perhaps by borrowing some principles from the successful large-scale AI community, while also charting completely new territories inspired directly by neuroscience.
So, what does this all mean for you, the listener? It means that the next generation of artificial intelligence could look radically different from what we see today. It could behave in ways far more akin to biological intelligence, learning continuously throughout its lifetime, making real-time decisions directly from noisy sensor data, fusing multiple streams of information with an efficiency that current systems can really only dream of. Imagine devices that adapt, that evolve, that learn from experience, rather than needing constant, costly retraining in massive data centers.
And this raises, I think, an important question for you to consider long after our deep dive today is over. If we do successfully bridge these gaps, the software challenges, the hardware integration, establishing clear, compelling benchmarks that truly capture its unique advantages, could neuromorphic computing finally unlock truly adaptive, continually learning machines? Machines that aren't just intelligent in a static way, but also self-organizing and dynamically reconfigurable, just like the incredible biological systems found in nature. That truly is the profound promise. That's what keeps researchers pushing the frontier of artificial intelligence in this direction.